Okay, so here are the solutions of the all tests that we have. First, we're gonna start with the first problem right here. So I'm just gonna rewrite this function as pi squared minus x squared plus pi to the power of x minus e times x to power negative 1/4 minus logarithm of x base 3. Then y prime is going to be equal to, be careful about this one right here, the first term is just a constant and the derivative of a constant is 0, minus the derivative of x squared is just 2x, plus pi to the power of x ln of pi, plus 1/4 e x to power negative 5/4 minus 1 over x ln of 3. And if you are wondering where this arrived, okay, that's just the derivative of, if you have negative e times the derivative of x to power negative 1/4 prime, this is just the exponent rule is negative e times negative 1/4 times x to power 1 less, which is negative 1/4 minus 1, bringing us to e times 1/4 times x to power negative 5/4. No need to simplify anything from here. Moving on to the second problem. Here, obviously, we have a product. This is going to be my function f, and this is going to be my function g. Just as a reminder, derivative of f times g is f prime g plus f g prime. So y prime is equal to the derivative of 3x squared plus 2 times e to the power of x minus 5 to the power of 7 prime times tangent of 8 e to the power of x plus 3x squared plus 2 e to the power of x minus 5 to the power of 7 times the derivative of tangent of 8 e to the power of x. Okay, so in order to solve these two, I need to use chain rule for both of them. So this function right here is this expression to the power of 7. Then the derivative is going to be 7 times 3x squared plus 2 times e to the power of x minus 5 to the power 6 times the derivative of the inner function 3x squared plus 2 times e to the power of x minus 5 prime times tangent of 8 e to the power of x plus 3x squared plus 2 times e to the power of x minus 5 to the power of 7 times derivative of tangent is secant squared of 8 e to the power of x times the derivative of the inner function. So again, I'm using the chain rule here, 8 e to the power of x prime. And I think we're done with this problem. 7 times 3x squared plus 2 times e to the power of x minus 5 to the power of 6 times the derivative of this function right here. That's 6x plus 2 times e to the power of x, derivative of 5 is 0, times tangent of 8 e to the power of x plus 3x squared plus 2 e to the power of x minus 5 to the power 7 times secant squared of 8 e to the power of x times this derivative here is simply 8 times e to the power of x. Moving on to part C. In part C, we just have the quotient rule. Derivative of the quotient rule is f over g. Prime is f prime g minus f g prime over g squared. And as I have said in class, simply square the denominator and leave it as such. X plus cosecant of x to the power 5. The whole thing squared. And now let's set up the quotient rule. Derivative of sine x cosine x times the denominator x plus cosecant of x to the power 5 minus the numerator sine x times cosine x times the derivative of x plus cosecant of x to the power 5 is equal to. Now here we will have the product rule right here, and here we will have we will use derivative of x is 1, and then for the cosecant function we'll have to use chain rule. Okay, so let's use the product rule right here. Derivative of sine is cosine, so cosine x times cosine x is cosine squared x, plus sine times derivative of cosine is negative sine, so minus sine squared x times x plus cosecant of x to the power 5 minus sine x times cosine x, and here, as we said, derivative of x is just 1, plus, or better said minus, because derivative of cosecant is negative cosecant. Now be careful here, you have this weird tendency to just to say negative cosecant cotangent, and then you write something like this without writing what's here. As we said again in class, that cannot happen. It has to be cosecant of x to the power 5 times cotangent of x to the power 5 times the derivative of x to the power 5, which is 5x to the power 4, and then in the denominator again you have just square the denominator and you're done with that. So cosecant of x to the power of 5, the whole thing squared. If somebody is wondering where this appeared from, I'm going to write it here. Derivative of sine of x times cosine of x prime, again that's the product rule, sine of x prime cosine of x plus sine of x times derivative of cosine of x. Derivative of sine of x is cosine of x times cosine of x. Sine of x derivative of cosine of x is minus sine of x, and then this is simply cosine squared x minus sine squared x. Exactly what we have here. Okay. Problem D. Okay, here we just have a very busy chain rule. So this is, I'm going to rewrite this as cosine of cotangent of ln of x. Then the cotangent is raised to power 1/2. That's the root. And then the whole function here is raised to power 3. And now it's more clear what is going to be the outside function, and then in each step we're going to find the derivative of the more embedded function. Okay, so let's start from the beginning. Y prime is equal to 3 times cosine of cotangent of ln of x, and that whole thing to power 2 times the derivative inside, which is cosine of cotangent to power 1/2, and the cotangent is of ln of x prime here. Okay, so 3 times cosine of cotangent of ln of x to power 1/2 squared times derivative of cosine is negative sine of square root of cotangent of ln of x, or that's cotangent of ln of x, but the cotangent is raised to power 1/2 times the derivative of cotangent of ln of x to power 1/2, and then here prime. Okay, so I have 3 times cosine of cotangent of ln of x to power 1/2 x squared times negative sine of cotangent ln of x. Cotangent is raised to power 1/2 times derivative of cotangent is negative cosecant squared. Oh no, it's to power 1/2, my bad, sorry. I forgot that exponent there. So times 1/2 times cotangent of ln of x to power negative 1/2 times the derivative of cotangent of ln of x prime is equal to negative 3. This negative comes from here. I take this negative and put it in front of the 3. No need to do that as long as you keep the parentheses right. So this is cosine squared of cotangent of ln of x to power 1/2 times sine of cotangent of ln of x to power 1/2. I can write this 3/2. That's this one right here. Times cotangent of ln of x raised to power negative 1/2 times derivative of cotangent is negative cosecant squared of ln of x times the derivative of ln of x. And finally, I'm going to write down the answer. Derivative of ln of x is simply 1/x. So I have 2x in the denominator. This minus and this minus, they cancel each other out. So I have 3 times cosine squared of square root of cotangent of ln of x times sine of square root of cotangent of ln of x times cotangent of ln of x to power negative 1/2 times cosecant squared of ln of x. And as I said, this is a very, very busy chain rule. I don't even know how many times we used it. 1, 2, 3, 4, 5 times. Which was made it a very complicated problem. Okay, moving on. Okay, this is a typical example of a function that is implicitly defined. So I have to use implicit differentiation. Okay, which means I'm just going to take derivatives right away on both sides. Ln of x minus y prime is equal to the derivative of x on the right hand side minus the derivative of sine of y. Okay, the right hand side seems easier right now. Derivative of x is just 1 minus derivative of sine of y is cosine of y. So don't forget to multiply by y prime because we are differentiating a function y that is defined in terms of x, except that we don't know what is explicit definition. On the left hand side, I have to use the chain rule. Ln, the outside function is ln of x minus y, so its derivative is going to be 1/x minus y times the derivative of x minus y. Okay, derivative of x is just 1 minus derivative of y is y prime over x minus y is equal to 1 minus y prime times cosine of y. And this is about finding the derivative. From now on is just some algebra in isolating y prime. So the left hand side will be 1/x minus y minus y prime over x minus y is equal to 1 minus y prime times cosine of y. Now identify the functions that include the factor y prime and bring them on one side of the equation, and everything else that doesn't have y prime bring it on the other side of the equation. Okay, that brings us to 1/x minus y minus 1 is equal to y prime over x minus y minus y prime times cosine of y, which allows us to factor y prime on the right hand side. I am left with 1 minus x minus y minus cosine of y. And here I can divide both sides by this factor right here, which will allow us, this factor right here, which will allow us figuring how much is y prime only. So y prime is equal to 1 over x minus y minus 1 over 1 over x minus y minus cosine of y. And because the function y was not defined explicitly in terms of x, the derivative y prime also is going to depend on both x and y. In other words, it's going to be expressed in terms of x and in terms of y. It's impossible to express y prime solely in terms of x. Moving on to the next problem. Here we have a function that requires logarithmic differentiation. How to recognize that? Well, you can see that I have a function in terms of x in the base, but also a function in terms of x in the exponent right here. So the first thing that we want to do is bring that exponent down, and how we're going to do that with the help of the logarithms. Ln of y is equal to ln of sine of x times arctangent of x. And now simplify, it means just bring this arctangent here by properties of logarithms, just bring it in front of the ln function. So I have arctangent of x times ln of sine of x. And now we move on to implicit differentiation, taking derivatives on both sides. Derivative of ln of y is y prime over y is equal to, here as we have said in class, expect to use the product rule. Okay, so I have derivative of arctan times ln of sine of x plus arc tangent of x times the derivative of ln of sine of x. So y prime over y is equal to derivative of arctangent of x is 1 over 1 plus x squared. So that's ln of sine of x plus arctangent of x times derivative of ln of sine of x is 1 over sine of x times derivative of sine of x, which is cosine of x. Okay, and that's about it with the derivatives. Now we just have to express y prime, that's equal to y times this whole expression here. And then don't forget, since y was described explicitly in terms of x, don't forget to write that as the final part of this answer. So y is sine of x, the whole thing raised to arctangent of x times, and now just bring this expression right here. Ln of sine of x over 1 plus x squared plus cosine of x times arctangent of x over sine of x. And this is the final answer. Okay. So So next problem is find the equation of the tangent line to this function right here parallel to this given line. Okay, so let's if I have two lines L1 and L2, okay, if they're parallel, that means that there are slopes that have equal slopes. Okay, so if the tangent line to this graph is parallel to this line, that means that the slope of the tangent line is going to be the same as the slope of this line right here. So let's first figure out how much is that slope. So from here we have that negative 2y is equal to negative x plus 2, or simply y is equal to 1/2 x minus 1. So the slope m is equal to 1/2. What does that mean? Since, one more time, the tangent line to this function is parallel to this line, that means that the slope of the tangent line is going to be equal to the slope of this line, which means that the slope of this tangent line is going to be equal to 1/2. But the slope of the tangent line is given as f prime of x is equal to 1/2. And that's what we are going to use. So what's missing here, right? Since I already know the slope of the tangent line, let's see, what do we miss? I have y minus y naught is equal to 1/2 times x minus x naught. Okay, I already have the slope of the tangent line from the fact that it's parallel to this line. So what's missing? I don't know at what point the tangent line touches this this curve, so that it has a slope 1/2. But this will answer this part right here, is the answer to our problem. So let's figure out how much is y prime. F prime of x is equal to derivative of x plus 2 times x to the power negative 2 prime. So f prime of x is equal to 1 plus 2 times negative 2 times x to the power negative 3. F prime of x is equal to 1 plus 4 over x cubed. And this expression has to be equal to 1/2. So let's solve that. 1 plus 4 over x cubed is equal to 1/2. X cubed plus 4 over x cubed is equal to 1/2. Cross multiplication 2 times x cubed plus 4 is equal to x cubed, right? So this multiplies by this and this multiplies by this. So 2x cubed plus 8 is equal to x cubed. 2x cubed minus x cubed is equal to negative 8. X cubed is equal to negative 8, or x is equal to cubed root of negative 8, and that's negative 2. So x is equal to negative 2. Recall that this point here, this x value, is the coordinate of the point that belongs to this curve, but also to the tangent line as well. So we have find x naught, that's negative 2, right? So we just have to find this one. As I said, the point belongs to this curve, so in order to find the y value of that point, I just have to evaluate how much is f at negative 2. That's negative 2 plus 2 times negative 2 to the power negative 2. That's negative 2 plus 2 over negative 2 squared. Negative 2 plus 2 over 4. That's 1/2 minus 2. Right? Because these two cancel out. And I get 1/2 minus 2. which is how much? 1 minus 4 over 2, and that's negative 3 over 2. And that value is our y value, negative 3 over 2. Once we have these two values, we can plug it in our equation of the tangent line and finally get y plus 3 halves is equal to 1 half x plus 2. Oh, this was a slightly different problem, because I was not given the point where I was looking for the tangent line, but I was given the fact that the derivative is 1 half due to the fact that the tangent line and this line were parallel. Okay, moving on. Now we have to find g prime and evaluate it at pi over 2. Okay, explicitly I don't know what my function g nor what my function f is, but I'm given this information right here. So in order to find g prime at pi over 2, first I have to find g prime. Now let's look at the function g. In order to find its derivative, we have to use the quotient rule to begin with. So g prime is going to be equal to f prime of x, the whole thing squared, times the derivative of f of sine of x prime times f prime of x minus f of sine of x times the derivative of f prime of x. Okay, so let's see what we have. In order to find this derivative, right here, I have to use the chain rule. So there's going to be f prime of sine of x times the derivative of the inner function, derivative of sine of x, times f prime of x, minus f of sine of x times the derivative of the first derivative is simply the second derivative of the function, over f prime of x squared. And now let's just find this derivative and finish with this problem. So I have f prime of sine of x times cosine of x times f prime of x minus f of sine of x times f double prime of x over f prime of x, the whole thing squared. And now I have to find how much is g prime evaluated at pi over 2. That's f prime at sine pi over 2 times cosine of pi over 2 times f prime at pi over 2 minus f of sine of pi over 2 times f double prime of pi over 2 over f prime of pi over 2 squared. And this indeed looks a little bit busy, but if you look at this fact right here, I have cosine of pi over 2, and I know that cosine of pi over 2 is 0. So if this is 0, that's going to make this whole product here 0. And we end up having 0 minus f of sine of pi over 2 is 1. So f of 1 times f double prime at pi over 2 over f prime of pi over 2 and the whole thing squared. And now in order to figure out how much is this, we'll look at these values given here. So f of 1 is 2. So 0 minus 2, f of 1 is 2, right? F double prime at pi over 2 is 3. f double prime at pi over 2 is 3. So negative 2 times 3 divided by f prime at pi over 2 is 2. From here, right? F prime at pi over 2 is 2, so 2 squared. And this finally is equal to, these two cancel, right? 2 and 2 cancels out. So negative 3 over 2. Okay, moving on to the next problem. Problem number 4, find the relative extrema. Okay, so here we're going to use the first derivative test. In order to do so, I have to find the critical numbers. In order to find the critical numbers, I have to find f prime. F prime of x is equal to product rule. X prime times e to the power of 2x plus x times the derivative of e to the power of 2x prime, which is equal to derivative of x is 1 times e to the power of 2x plus x times derivative of e to the power of 2x is e to the power of 2x times derivative of 2x. So I have e to the power of 2x plus this derivative is just 2x e to the power of 2x. And you should expect a question like this on the test or on the final, where you have to not only find the first or the second derivative, but also simplify it a little bit. So I have to solve this as being equal to 0, or where it does not exist. So f prime equal to 0, that means that e to the power of 2x, 1 plus 2x is equal to 0. I got this expression just by factoring e to the power of 2x. So that's just the first derivative. Here, be careful, this factor here is never 0, which leaves us that only this factor can be 0, and that factor is 0 when x is equal to negative 1/2. Also, f prime of x exists for all the real numbers, which means there is no value of x where the first derivative would not exist. Why is that so? Well, e to the power x is defined on R, and then the other multiplicand is just a linear function, a polynomial, which is defined also everywhere. Okay, if the domain, of course, you should always start with the domain of this function. By the similar logic, right, x is defined everywhere, e to the power 2x is defined everywhere, which means there the product is defined on R, so the domain are all the real numbers, and now that means that from negative infinity to positive infinity, the only critical number is negative 1/2, and we're going to create that table. You have from negative infinity to negative 1/2, and from negative 1/2 to infinity, y prime and y. Okay, if I look at this product here, okay, I can see that this factor is always positive. This factor is always positive, so you can simply ignore it in the following calculation, in building this table. So for all the values less than negative 1/2, say, I don't know, negative 1 plus 2 times negative 1, that's 1 minus 2, so that's negative, which means the function is decreasing. Take 0, 1 plus 2 times 0 is 1 plus 0, which is positive, so the function is increasing. And here what do we have? We have a minimum, so relative minimum is f of negative 1/2. Be careful, I'm evaluating the function f, and that's negative 1/2 times e2 times negative 1/2. Negative 1/2 times e to the power negative 1. You can write it like this or like this, really doesn't matter. These two cancel out, that's how we got e to the power negative 1. And this is the relative minimum. And then there is the typical question of the finding the tangent line at a given point to a curve defined explicitly. So let's see what do we have. This function right here, this equation, sorry, in order to find the derivative, just simply find the derivative of every single term. Okay, this should be easy. Maybe the only problem would be this one right here. So let's see what the derivative is. 3 times 2 times x to 1 power less plus 5 times, here I have to use the product rule, so derivative of x times y plus x times derivative of y plus 4 times y prime over y is equal to derivative of 2 is 0. Okay, so 6x plus 5 times derivative of x is 1, 1 times y is y, plus x times y prime plus 4y prime over y is equal to 0. Now, let me just remind you what we were looking for. We were looking for the equation of the tangent line at a given point, so that's y minus 1 is equal to f prime evaluated at negative 2 and 1 times x plus 2. So I want this expression right here. In order to save time, I don't have to isolate y prime in terms of x and y, where I can just simply evaluate this expression at the point 2 and negative 1. So I get 6 times negative 2 plus 5 times negative 1 minus 2 times y prime plus 4 times y prime over negative 1 is equal to 0. So negative 12 minus 5 plus 10y prime minus 4y prime is equal to 0. Here I have negative 17 is equal to negative 6y prime, or simply y prime is equal to 17 over 6. And that's how we have found the slope of this tangent line. The equation of the tangent line is going to be y minus 1 is equal to 17 over 6 times x plus 2. And the last problem, we have to sketch this graph. Okay, right away. Oops, nope, not that one. Right away, I just sketch the coordinate system, and every single thing that I'm gonna find, I'm gonna plot in here. Start with the domain. This one right here, x is defined everywhere. Okay, let me just show you this. Y is equal to x times cubed root of x minus 5 squared. That's my function, right? And because of this cubed root, I can find cubed root of negative numbers and I can find cubed root of positive numbers. So that means the domain is going to be R. Okay, so this function is going to be defined everywhere. Right away, I told you in class, if the domain is R, that means right away we don't have vertical asymptotes, which is very important, okay? No vertical asymptotes, okay? So then what are going to be part A? What are going to be x-intercepts? That means put y is equal to 0, x times x minus 5 to power 2/3 is equal to 0. The way the problem is given to you, you can easily see that the product between these two factors is 0 when either one of them is 0, either x is 0 or x is equal to 5. So 1, 2, 3, 4, 5. The first 2 points on this graph is right here and right here. The x-intercepts. If the x-intercepts goes through the origin, that's right away you have the y-intercept as well, because there is impossible to have more than one y-intercept, so also 0, 0. Okay, so we have found the x and the y-intercept in A. Although in this question you're not asked to find horizontal asymptotes, I'm just going to calculate this limit in order to know what happens with my function as we send x to positive or negative infinity, okay? So the limit of x times x minus 5 to power 2/3 as x goes to negative infinity. Okay, so let's see what happens with this limit. This one goes to negative infinity. If you don't see it right away, well, this is x times cubed root of x minus 5 squared as x goes to negative infinity. So be careful, this here, because of the exponent, goes to positive infinity, and we said this goes to negative infinity, so the product is going to be simply negative infinity, which means what? As x goes to negative infinity, the function drops down to negative infinity. So we're going to start sketching it from somewhere here. Similarly, as x goes to positive infinity, this function, this factor will go to positive infinity. This also always goes to positive infinity because of the square here. So the answer is positive infinity, which means that when we're going to end sketching the graph as x goes to positive infinity, the function will blow up to positive infinity right here, okay? So we have somewhat better understanding where to start sketching the graph, and where to end sketching the graph. And this graph is going to go throughout the whole coordinate system because it has no vertical asymptotes, or simply because the domain is R. Okay, so let's get rid of this now. We don't need it. We just used it to realize where the function is going to start and where the function is going to end. Okay, next is part B, intervals where the function is increasing and decreasing. So bring in the first derivative here. So I have f prime is equal to 0. Look at the numerator, which means 5 times x minus 3 is 0, which means x is equal to 3. Cannot be easier than that. F prime of x does not exist. It will not exist when the denominator is 0, so 3 times x minus 5 to power 1/3 is equal to 0, which means x is equal to 5. Okay? The first derivative being equal to 0, what does it say? It has horizontal tangent line. If the first derivative does not exist, it means that we have vertical tangent line. Okay? So x is equal to 3. When x is equal to 3, I have horizontal tangent line. Let's sketch the point or plot the point where we're going to have horizontal tangent line. F of 3 is equal to 3 times 3 minus 5 to power 2/3, which is equal to 3 times negative 2 to power 2/3, which is equal to 3 times 2 to power 2/3. And why this is equal to this? Because negative 2 to power 2/3 is equal to cubed root of negative 2 squared, which is cubed root of negative 1 squared is simply 1. So that's 4, which is cubed root of 2 squared. And this is how I get this part, right? And that approximately is equal to 5. So that's why this information was given to us. So 1, 2, 3, 4, 5. At this point here, another point on the graph, I also have horizontal tangent line. Okay, at 5, I have a vertical tangent line. So let's remind ourselves, what does it mean for a graph to have a vertical tangent line? The graph can be, sorry about that. The graph can be like this, or like this, or like this, or like this. And it's going to depend on what? It's going to depend on how the function is going to behave, and we're going to get that from creating that table. So from the fact that domain is R, we have from negative infinity to 3, from negative infinity to 3, from 3 to 5, and from 5 to positive infinity, y prime and y. Okay, here in y prime, in f prime, there is not a single term that can be ignored in terms of whether that is always positive or negative, maybe except 5 and 3. Those are not really playing any role. Let's choose the point 0 here. 0 minus 3 is negative, 0 minus 5 is negative. Negative divided by negative is positive, which means the function is increasing, and we expected that how else to connect these 2 points, right? From 3 to 5, we can choose the point 4. 4 minus 3 is positive, 4 minus 5 is negative. As you can see, I'm not really thinking about this cubed root, because cubed root of negative number is negative and cubed root of positive number is positive. So 4 minus 5 is negative 1, negative. Positive divided by negative is negative. The function is decreasing, which means I have a local maximum at 3. So this point here is going to be local maximum. And finally here I can choose the point 6. Six minus 3 positive, 6 minus 5 positive, positive divided by positive is positive. The function is increasing. And now, as you can see, the function decreases before 5, and from 5 onward starts increasing. So this is the only option that we have from here. The other ones simply don't work. Okay, so this is how I'm going to sketch this graph, and the function has a local minimum at 5. So this point here is local minimum. Okay, and finally we have to talk about concavity. In order to do so, let's look at the second derivative. Let's get rid of all of this calculation here. Okay, bring in the second derivative. So f double prime is equal to 0. F double prime does not exist. The second derivative is 0 when x is equal to 6, and it doesn't exist when x is equal to 5. Because the domain is R, you build this table from negative infinity to 5, from 5 to 6, and from 6 to positive infinity, y double prime and y. Here, the problem is going to be significantly easier. Well, significantly, it's going to be a bit easier than when we're checking the first derivative. Why? Because this term here is positive, this term here is positive, and because the denominator is raised to power 4, you can ignore the denominator in checking the sign for this derivative. And then what do we have? Well, any number less than 6 minus 6 is negative. The function is concave down. In this interval here, for any number less than 6, all the numbers here are less than 6, minus 6, that's negative, it's concave down. And finally, for this one, for all the terms, for all the numbers greater than 6, that difference is going to be positive. So this is positive, so it's increasing. It's concave up. So I have inflection point. It's f of 6, and I'm going to let you figure that f of 6 is equal to 6, 6, not 5. So at 6, and here I have 6. And what do we have here? So the function is increasing. This might be slightly misleading here. Sorry. So it's concave down and it's increasing, reaching the minimum, starts decreasing, reaches this vertical tangent line, starts increasing, and here changes finally concavity and going to positive infinity. So here is the graph of our function. And as you can see, everything is sketched out. The function is concave down from negative infinity all the way to 6. It's concave down here, and then changes concavity and explodes and it goes to positive infinity. And that's how we have answered all of these parts for this question.